for these experiments, we were really looking at flash heating. So a lot of the work that I'm going to show you guys today is from my dissertation work. And so we were looking at flash heating using context scale history. And so John gave a really good intro to this last week, but I'm going to kind of go over it again, even though I know everyone in this audience is pretty familiar with dynamic weakening in general. But we've seen in laboratory experiments that we have dramatic weakening from high initial friction that matches more or less Barbery predictions to friction coefficients approaching about 0 as slip displacement increases. And so here you can see this figure from Detoro et al. Nature 2011, which is kind of obviously a classic paper in the field, where we have that decay from our high peak friction with increased sliding and initial low velocity, increasing velocity at intermediate acceleration in these experiments. We eventually reach a low steady state friction. And if we isolate those steady state friction coefficients, we can see that once we get up to seismogenic rates of about 1 meter per second, we have dramatic reduction across a wide range of lithologies. And I know there was a great talk at Gordon this year, if you were able to make it. There's a long list of dynamic weakening processes that we've used to account for this. And the whole concept of dynamic weakening is one of the ways that we've postulated it could explain some of the geophysical and seismological observations of earthquakes. And having seen it in the lab, it seems like it's a promising explanation for a weak fault. And so of all the mechanisms that have been suggested, probably the two that are most robustly looked at in the lab are thermal pressurization and then flash weakening of asperity contacts. But there's others, there's mineral dehydration, decarbonation, silica gel weakening. These are just a few. I think the total's 20 at this point. But this work is really focusing on flash heating, mostly because flash heating, it happens in the early stages of sliding. And so using the apparatus at A&M, we can really hone in on that particular process. And so just as a brief overview of what flash heating and weakening is, it deals with disparity scale contacts. And so the idea is that faults are not perfectly planar. They have roughness, and the load is supported not across the entire macroscopic surface, but inside of these microscopic asperity contacts that have high stress concentrations, both normal stress and shear stress, that once SIP initiates, you get high temperature increases at those asperity contacts. So as that temperature increases, eventually you pass a breakdown or weakening temperature. So above this breakdown temperature, that contact strength is going to begin to thermally degrade. And so Rice developed a constitutive equation set in 2006 is when he published, this classic work that predicts what the friction coefficient is going to be based on your quasi-static friction, a fully weakened friction coefficient, your sliding velocity, and then a weakening velocity, VW. And so that weakening velocity is really what's key. If you're sliding above that weakening velocity, you get immediate weakening of those asperities. Below it, there's no weakening at those asperity contacts. And that weakening velocity is a function of material properties. So your thermal properties of the material, your specific heat, your heat diffusion, density. It's also a function of the temperature, the macroscopic temperature of the fault surface. So that's TL here. That breakdown temperature, T1, which is going to be material dependent, your contact shear strength, and then the asperity dimension. And we usually assume that asperity contacts are about on the order of 5 microns, but that's one of the big unknowns with flash weakening models. So with that in mind, in experiments at intermediate slip rates, they're mostly rotary shear apparatus, although with Juan and Prakash, those are a different experimental setup. What we see in all of these plots here from Goldsby and Tolis 2011, flash weakening model is shown in red lines. Data from experiments are shown in your various other dots and lines. And we see pretty good agreement between the laboratory data and the model at these intermediate accelerations, which is great. But we also see in other experiments. Here, again, we've got friction coefficient plotted versus velocity. And these are some experiments that were done by Brooke Proctor, published in 2014 on antigrite, gouge, and bare surfaces. And what they saw is that during the acceleration phase, so here, this black line is the flash weakening model, the red is the experiment data. In this acceleration phase here, there's a pretty good overall agreement, but there is transient and hysteretic friction that's not captured by the model. And then during the deceleration phase, you can see that there's a large deviation between what we observed in the lab and what the model predicts. In this case, the model predicts it going back along the exact same path. And so one thing that Proctor et al. Did was incorporate increasing surface temperature into their work. And so when we did that, they saw that the fit particularly during the first initial stage of deceleration was much more improved, but there's still a large deviation from what the model predicts versus what we see in the lab. And so we're really wanting to investigate this a little bit more in the work I did for my dissertation. And we knew that this deviation from model predictions, it likely reflects a few things: your millimeter scale contacts that are evolving, your asperity contacts, which are evolving, your localization along the sliding surface that develops during sliding and during the deceleration, but then also changes in local surface temperature. And this work by Proctor et al. Emphasized that surface temperature was a really key component. And so we wanted to explore particularly changes in surface temperature in a little more detail. So to do that, we use the high-speed biaxial apparatus at Texas A&M. So here on the left is a photo of the apparatus. This is a 6-foot ladder for scale. On the right, we have a little bit more of the details of the apparatus. We use a hydropneumatic loading system to drive our piston, which is right down, and move a moving block between two stationary blocks. We'll look more at the sample assembly bit in the next slide. We also use a horizontal hydraulic loading system to apply, we use this hydraulic loading system to apply our normal stress in our experiments. And then what's been particularly novel is using this high-speed IR camera that we use to actually image our blocks and measure surface temperatures during experiments. And that's really been the big advancement from this work. So we have that moving block, we have our IR camera. The piston drives this moving block between these two stationary blocks, so it's a double direct shear configuration. And using that high-speed IR camera, we use a mirror to bend the light path and image our moving block directly after it comes out of contact with the stationary block. So we can't image it when our two blocks are together, but the moment that moving block emerges from contact with the stationary block at the bottom of the block, we can image the sliding surface and try to measure surface temperature. And so in all of our experiments, we used a macroscopic normal stress of about 9 megapascals. And then we did velocity steps from 1 millimeter per second up to 900 millimeters per second. So I have a short video that actually demonstrates one of the experiments. It's a little loud. Those pings are sticks of events that happen during our quasi-static sliding. And then we have almost an immediate jump as we slide at a meter per second. So one thing we noticed in initial experiments on flat surfaces is that we developed contacts, but we didn't know the history of those contacts during sliding. And that has big implications for our heat generation rate. So what we wanted to do in these experiments in particular was to develop a particular geometry where we knew precisely the millimeter scale sliding history. And so we developed this geometry that involves a series of grooves and flat top ridges on our sliding surface. And so this is an instantaneous view of what our surfaces look like. White are ridges, gray are grooves on the moving block, red are grooves on the stationary block. So when we mate our samples together, we have these diamond looking like contacts. Those are in contact, everything else is out of contact. So only 25% of our sliding interface is in contact at any time during sliding. And we image an area that's initially fully in contact with the stationary block, but at the end of our experiment, as it's come out of contact, we can image about a whole ridge, which is really great. It gives us a lot of IR data. And so using this setup and using that geometry is particularly powerful for some of the modeling that I'm going to talk about later. Since we have this prescribed geometry, we can divide the ridges on the moving block that I'm imaging into individual elements. And for each element then, because I know the geometry of the moving block and the stationary block when they're mated together and when they're sliding, I can calculate the precise sliding history for all of these model elements I'm using during sliding. And so these are what I'm going to really fold into some of the modeling I'll talk about in a bit that's made it quite powerful to model flash weakening. And what's really great about this geometry is that because of the symmetry involving the ridges on the stationary block and the moving block, the sliding history of this ridge here I've isolated with these dashed lines is the exact same as the ridge next to it and the ridge next to it. So all of the ridges on my moving block experience the exact same sliding history. So in theory, that means that the temperature distributions from one ridge to another should be the exact same because they have the same millimeter scale sliding history. So that gives you an idea of basically our experimental setup. When we look at the data, we see to some extent what we expect to see. So here on the left, we've got the friction coefficient, plots for friction coefficient versus displacement from one of our experiments. It's just a representative experiment. You can see before the velocity step is in light gray. This in white is after the velocity step. So we have initially high friction coefficient of about 0.72. After we initiate that velocity step, we decrease and weaken within a few millimeters of sliding, about 1 to 2 millimeters after reaching our peak velocity, which in this case was about 900 millimeters per second. And after that initial weakening, we maintain relatively constant strength sliding for the rest of the experiment. And our normal stress is relatively constant, plus or minus 10% during all of the experiments. And so this is basically what we expected to see. We get dramatic weakening at almost a meter per second sliding. And that matches observed data from other experiments. Now, what's really novel again is some of our temperature data. So here are some results from a few of our experiments. The first thing that we notice is that the temperature is quite inhomogeneous across all of our sliding surfaces. It increases as a function of displacement. So when you look at these thermographs, on the left, this axis here, this is showing displacement after the velocity step. So contacts here at the bottom of the thermographs really represent contacts that emerged early in the experiment. So they weren't in contact, they experienced fewer total lifetimes and didn't get quite as hot. Whereas contacts at the top of the thermograph, those were sliding for almost 30 millimeters, the full amount of displacement in the experiment. And so they get hotter. So temperature increases with cumulative displacement, but we can see that the temperature distribution on adjacent ridges, it's very different between all of our experiments. And so because of that prescribed millimeter scale sliding history geometry that I use in the experiments, in a perfect world, the temperature distributions would be the exact same on all of our ridges. So seeing that that's not the case, even though the millimeter scale sliding history is known and the same, gives us an idea that there must be some sort of inhomogeneous stress distribution in these experiments. And so we're going to explore that a little bit more. The other thing, though, I want to point out is we get repeated hot spots in all of our experiments. So you notice here we have some of these here in red. Those are about 300 degrees C. 1 millimeter, roughly equivalent hotspots that occur in our experiments. We see them in all of our experiments, and we also see them repeating between experiments, which has been pretty interesting. And particularly in the later section of this talk, we're going to talk more about those hotspots. So I have these temperatures. What I really want to do is use some thermal modeling to model temperatures and compare to our measured temperatures, because we have the idea that these inhomogeneous temperature distributions really reflect inhomogeneous stress at the millimeter scale across our sliding surface. So we used a relatively simple 1D heat conduction equation where we calculate our temperature as a function of our ambient temperature, 20 degrees C, a heat generation rate, Q, and then some thermal properties of the material. Now, what's really useful with that sliding geometry I talked about earlier is we can turn our heat generation rate off and on. Since I know the millimeter scale sliding history, during rest times, I set that heat generation rate equal to 0. During lifetimes, that heat generation rate becomes the product of our macroscopic normal stress, so 9 MPa, our friction coefficient, and the sliding velocity. And so this is an example from a pixel that I modeled temperature for. This experienced a partial lifetime, so our temperature increases during that partial lifetime. Then a rest time, when it's out of contact, that heat generation rate goes to 0, and so we get a decrease in surface temperature. Then that contact experienced another full lifetime, so temperature begins increasing again, a partial rest time, then it emerges. This is when we would start imaging it. It slides a little bit more, and then this is the end of sliding. And so in this model, we'll have the temperature increase when contacts are in contact, and then decrease whenever ridges on that moving block abut a groove on the stationary block. So really it's taking into account the sliding geometry of both the moving block and the stationary block, but I'm only modeling points on that moving block where I'm imaging and measuring surface. And using that model and considering the inhomogeneous surface temperature. So like I said, we think that that might reflect inhomogeneous normal stresses. So on this thermograph here that I showed a little bit earlier, we have these 3 elements that I identified, A, B, and C. All 3 of these elements are in the exact same position on a moving block ridge, and so they experience the same sliding history during the experiment, but they have vastly different temperatures. So it varies by about 150 degrees C. So with that knowledge, we have the idea that, okay, lower temperatures reflect lower local normal stresses, higher temperatures reflect higher local normal stresses. So I wanted to fold this into our model. So we have, again, the same temperature equation. We're still turning that heat generation rate on and off, but instead of using the macroscopic normal stress of 9 MPa, we're going to use a local normal stress. That's some factor of our macroscopic stress. So it could be half of the macroscopic stress, or it could be 10 times the macroscopic stress. And because we're dealing with temperatures, one thing we wanted to consider was that our local friction coefficient that we use in this heat generation rate is going to be changing as our temperature changes. So higher temperatures, we should have a slightly lower friction than our lower temperatures. And we wanted to incorporate that temperature dependent friction using Rice's flash weakening model. So we calculate a local friction coefficient using our quasi-static friction that we measured and recorded from our mechanical data. It was about 0.72, a fully weakened friction coefficient, and then again our velocity, and then a weakening velocity. And for the early stages of this modeling work, when we calculated that weakening velocity, we just used one parameter to represent the material properties, and we used the same values that Rice used in his original work from 2006. So really, when we're calculating that weakening velocity, we're just using one simple material parameter, and then our breakdown temperature, our weakening temperature, and then our modeled surface temperature. And again, this weakening temperature, we also used the value from Rice's original 2006 equation. So when we do this kind of modeling, these are some of the results. So again, it's the same thermograph here on the left where we have those pixels A, B, and C that have the same millimeter scale sliding history. And so I did a parameter search to figure out what the best local normal stresses were that would predict the temperatures measured at each of these elements. So here in yellow, this is our element C that had the lowest temperature. In orange, it's our element B that had our intermediate temperature. And then in blue is our element A, which had the highest temperature of those that we looked at. And so I don't have the temperature record during sliding because that moving block is hidden behind a stationary block, but I can record decreases in temperature after the end of sliding. So the dots here all represent measured surface temperature after the after the moving block emerged from contact with the stationary block, and then as it sat there and slowly cooled after the end of sliding. So this point represents when it emerged. This gray line here is the end of sliding, and the rest of the dots on all three of these lines represent cooling data. And so for that lowest stress that low temperature contact, the best fit to the data was a local normal stress of about 4.3 times the macroscopic stress, so about 36 megapascals. And it was a pretty good fit to the data. The intermediate one, same thing. We had a good fit between model and our data, and it's an intermediate stress value, approximately 75 megapascals. So that was great. For that high temperature contact A, so this one is close to 300 degrees C, is a slightly different scenario. When we used a constant local normal stress, we weren't able to get a great fit between the measured data and model predictions. So we wanted to consider two alternative scenarios. One where our local normal stress is increasing with sliding, the other where it's decreasing with sliding. And what we saw is that if we have a local normal stress that's decreasing with sliding, we get a better fit between the cooling data. And this makes some sense. These contacts that have high temperatures also probably have high wear rates. And so because of those high wear rates, they may have a reduction in that local normal stress with sliding. And they're gonna have much higher wear rates than those intermediate and low stress contacts. So this probably reflects wear processes, but one of the good things we noticed when we did this analysis was that during sliding, the increases and decreases in temperature don't vary much between all three of these scenarios. And so we decided that even though from the data, it looks like our local normal stress is changing during sliding, it's really only impacting the cooling. And we're most interested in what's happening during sliding to eventually model /weakening. So we decided that using a constant normal stress model, at least during sliding, is a good enough fit. And just to give you an idea of what the data looks like, here we have temperature again, so the same plot here in the center. This is our local friction coefficient that's changing based on the Rice model. And here's our heat generation rate. So what we see is that as temperature increases, this is a lifetime, we get a decrease in our local friction coefficient and a decrease in our heat generation rate, which makes sense as that friction is locally decreasing with higher temperature, it's going to generate less heat. Then during a rest time, when that moving block point is out of contact and it abuts a ridge on the stationary block, our heat generation rate immediately goes to 0, and the strength of that contact begins to increase, and the temperature begins to decrease. And so then there's this cyclic history of temperature increases during lifetimes, decreases during rest times, that's combined with decreases and then increases in our friction coefficient. So having done this validation step, we wanted to apply this to all of our results. And so I used that sort of modeling procedure. I can't iteratively go through and try to solve the unique local normal stress for every contact on the surface. So instead, we chose ranges of local normal stresses that were 1/2 of the macroscopic stress of 9 megapascals up to 40 times our macroscopic normal stress. And so for each range, I looked at 15 in total of local normal stress values we modeled. I generated a synthetic thermograph. So this is an example of one of our synthetic thermographs where my local friction coefficient in this case was equal to the macroscopic friction, or I'm sorry, my local stress was equal to the macroscopic stress. So a stress of 9 megapascals. And these are the temperatures that the model would predict. So I had then 15 thermographs, synthetic thermographs for each of my measured thermographs that I compared to the measured data, and I used to contour stress on the millimeter scale. So here, these contours don't represent local normal stress, but they're stress factors. So there's some multiple of our macroscopic stress. So this 16 here represents 16 times our macroscopic stress of 9 megapascals. Which is quite high, obviously. And so the first thing that jumps out at us when we did this work was that we have huge stress concentrations at these hot spots that we see in our thermographs, which is what we expected to some extent. those temperatures are elevated because the stress is elevated. And we see low temperature regions reflect low normal stresses. But I don't have just one thermograph. For each experiment, I have 10. So I used individual thermographs to construct a composite thermograph with all of the recorded data from each experiment. And then I contoured stresses for the entire duration of the experiment. And so that's what I'm showing here. So on the left, this is the composite thermograph. These are all of my measured temperatures during one of my experiments. You can see that I don't really record any temperatures before 10 millimeters of sliding. And in this case, I was only imaging temperatures between about 100 and 300 degrees C. So I'm not able to record anything less than 100 degrees C. That's one reason that I used multiple temperature ranges in these experiments. But the first thing that I want to say, so here, these points again emerged early in the experiment, whereas regions up here, these contacts emerged much later in our experiment. So they experienced almost 30 millimeters of slip. These early contacts only experienced 10 or 15 millimeters of slip. If we zoom in at those contoured contacts, what we see is that those early contacts, even though they have lower temperature, the local stress concentrations are much higher. So here we get stresses exceeding 24 times our macroscopic stress of 9 megapascals. Whereas in those later stages of slip, even though our contacts are hotter, the stress concentrations are lower. Here, our peak stress concentration was about 12 times the macroscopic normal stress of 9 MPa. So there's an increase in surface temperature with sliding. But interestingly, there's this transition from high local normal stress contacts at the beginning of slip to low stress contacts at the end of slip. And so the majority of the load initially is carried by those high stress contacts during sliding, but then is more distributed and eventually carried by lower stress contacts in the later stages of sliding. And really, we think that this reflects wear processes that are happening at our contacts. So this is another way to basically look at the same thing. Considering I had all of those stress contour data, what I did was calculated changes in area percent in all of my image thermographs. So I wanted to look at how those stress contours were changing as a function of displacement in all our experiments, across all the experiments we did. So in all of the thermographs, it totaled about 112. I measured area percent for different contour stress factor ranges. So here, this plot represents contacts where the local normal stress was greater than or equal to 18 megapascals or less than 36 megapascals. So greater than 2 times my macroscopic stress or less than 4 times the macroscopic stress. And we see that these contacts have an increase in area percent as a function of displacement, and we don't really see any of those contacts before about 16 millimeters of sliding. Whereas some of our higher stress contacts are decreasing in area percent as a function of slip. So here we've got contacts with local normal stress values that vary from 8 times to 10 times the macroscopic stress. And so each data point represents a measurement from a single thermograph. And again, it's the same thing we saw in the previous form, just looking at the contour thermograph. It's just another way to look at the data. And we see that there's that decrease in local normal stress as a function of displacement. So here, this plot is showing area percent. So it's all of these linear regressions I have for all the ranges of local normal stress values I looked at. Plot is a function of displacement. And so those ranges were combined here into these various colored sections. So red represents our highest local normal stress ranges, here exceeding 20 times the macroscopic stress. Blue is our lowest, where our local normal stress was greater than the macroscopic, but less than 2 times our macroscopic normal stress. And so in the early stages of sliding, only half of the surface is in contact, and those contacts have high local normal stresses. But as sliding increases, there's an increase in contact area, approaching almost the entire ridge area by the end of sliding. And we're getting more and more low stress contacts and fewer high stress contacts at the end of sliding. And this really, we think, is reflecting wear processes that are happening on the contact surface. These high stress contacts get worn down, new low stress contacts adjacent to them come into contact. And so it suggests that wear processes are going to be important. But with this information, with this evolution of millimeter scale contact history, what we wanted to do is fold it into the flash weakening equation to model flash heating. But we wanted to make sure that this evolution held over different conditions. And so we repeated these experiments, these high-speed double direct shear friction experiments, but we used an additional contact geometry where we decreased the size of the grooves. So here the lifetimes or the groove dimension was equal to our ridge dimension. Here we decreased the ridge dimension by half, which really means that these contacts on this geometry with smaller rest times are going to be in contact 50% more. So they should get hotter, they should weaken more. So that's one way we varied the experiments, but we also looked at different velocity paths. So we did some more experiments using the same velocity step to 900 millimeters per second, but we also did velocity steps to 700, 600, and 300 millimeters per second. And we looked at an alternative velocity path. We did some experiments where we decreased the velocity from 700 millimeters per second at the beginning of sliding, and then it slowly decreased to 0. And so this way we could verify that this evolution of local normal stress holds up over different experimental conditions. And so looking at the mechanical data, we saw much what we would expect to see. So in this plot on the left, we have velocity, friction, and normal stress plotted as a function of displacement. We see that with increasing velocity, our magnitude of weakening increases, which is what we expected to see from previous experimental work. It's sliding faster, it's getting hotter, it's going to weaken more. That's great. When we compare results from those two different sliding geometries, so we have the one where we have short rest times that are in contact more often should get hotter. We see that indeed, as we would expect, our friction decreases as that rest time, that period where it's out of contact, is decreasing. So here on this figure A, we've got friction versus displacement. These are average results for all of our experiments at 900 millimeters per second, constant velocity. The black solid line is the geometry where our lifetimes are equal to rest time. So those are our long rest time experiments. The dashed lines are our short rest time experiments. And there is a significant decrease in our steady state friction coefficients as that rest time decreases. And we see the same thing at slower velocities. So in our 300 millimeters per second experiments, we saw the same thing. Our friction coefficient decreases more as we have those shorter rest times. So shorter rest times, more heat generation, lower friction, which is great. From this thermography, we again see that temperatures are inhomogeneous. We still develop these 1 millimeter squared equant hotspots. In all of our experiments, all the velocity paths we used, all the different peak velocities we used. So that was interesting. And we still see repeating hotspots. As our rest time decreases, it's a little hard to see in a schematic like this, but both the average and peak surface temperature is increasing in these shorter rest time experiments, which is what we would expect, particularly from the mechanical data and what we were hoping to see. So this is all wonderful and great. These hotspots are particularly interesting, and I'm going to come back to them in a couple slides. But using now these additional experiments, these additional conditions, we repeated the modeling that we did in our previous work. So I used thermographs. I generated synthetic thermographs for different local normal stress concentrations. With those synthetic thermographs, I contoured thermographs and then updated those linear regressions where I'm characterizing changes and stress concentration as a function of displacement. And so here, this is just an example of one of the stress one of our temperature maps that's been contoured. Again, we see those high stress concentrations at our high temperature hotspots. And when we compare new results to our previous data, so here, previous data is shown in the blue dots. All the other data points represent new experiments at different velocity conditions, different sliding surface geometries. And we see good overall agreement between all the experiments. There's no significant variation with either decreasing rest time or varying velocity path or varying peak velocity, which is great. So we updated those linear fits, and we now have these different linear regressions that we want to ultimately fold into the flash weakening model. But before we jump into the flash weakening model, one thing we wanted to consider were those high stress hotspots. So going back to Jim Rice's flash heating equation, when you calculate the weakening velocity, these thermal properties, so your thermal diffusivity, your specific heat, your density, those aren't really going to change as a function of temperature or contact size. If we think about the traditional asperity contacts, where they have a dimension of 5 microns, a contact shear strength of 3 gigapascals, the denominator in this flash weakening model is about 45 terrakilograms per second squared. If we think about these millimeter scale hotspots that we're seeing in all of our experiments, we know they're about 1 millimeter squared in diameter. If we assume that they have a contact shear strength of 100 megapascals, which we've measured and we've calibrated with our modeling and our thermography, if we make the assumption that those contacts are critically stressed and that the measured normal stress is close to their contact shear strength, then the denominator, if we consider those millimeter scale contacts in the flash weakening context, is 10 terrakilograms per second squared. But that's nominally different from asperity contacts. So we kind of decided to entertain the notion that we have weakening not just at our asperity scale, but for those high stress contacts, we have weakening at the millimeter scale too. And so in our flash weakening model approach, we're going to consider the traditional asperity scale weakening, but we're also going to consider millimeter scale weakening only at these high stress 1 millimeter squared contacts. So using those linear regressions that I showed a couple slides ago, we updated fits from our previous work where we characterize changes in local normal stress as a function of displacement. And we want to fold this into a flash weakening model, but we're going to make a couple small changes. One, just for computationally easier reasons, we decided to divide the sliding surface into 4 equal area regions. So instead of trying to model all 15 local normal stress ranges that I measured, I'm just going to model these 4 regions. And so then for each region, I can calculate a moving average for stress as a function of displacement. But for this region 4, this region has those high stress contacts. So region 4, we're going to divide into 2 different scales. One where weakening happens at the asperity scale. So these are for contacts with local normal stress values less than 12 times the macroscopic, so less than 108 megapascals. For anything with stress concentrations above 108 megapascals, so these light orange through the yellow, we're going to make the assumption weakening is happening at the millimeter scale. And so weakening can only happen at the asperity or millimeter. There's no double dipping, and we separate it that way. So then for each region, I have a moving average for local normal stress. And then again, for region 4, I have 2 moving averages, one for contacts that are weakening at the micron scale, others for contacts that are weakening at the asperity scale. And I calculate area percent to accompany that local stress value. For the bottom 3 regions, since it's only weakening at the asperity scale, it's always equal to 6.25. For the millimeter and micron scale regions, for the micron scale weakening, it's an increase with displacement. For the millimeter scale weakening, those high stress contacts, they're actually decreasing in area percent with displacement. So I have these distributions now, and these distributions are what I'm going to throw into a flash weakening model to model weakening. And in that model framework, I know this is plots with tons of math is not always easy to look at, but just so that you guys understand and are with me with the model flow, we calculate our friction coefficient by summing the products of all of our 5 regions and dividing by our macroscopic normal stress of 9 MPa. So I use all of these parameters to fill out my area indice, my local stress, and local friction. And I use the same model flow that we talked about earlier, where I'm calculating a local friction coefficient using the flash weakening equation. Here we added one new thing to our model, which is we used a rate and state equation to update our quasi-static friction coefficient in our model. For weakening velocity, we again use the standard Rice equation, but now we're using material properties for Westerly granite, which is what we did all of our experiments on. For our local surface temperature, we use the same equation that I talked about earlier for regions that are weakening at the micron scale. For the millimeter scale, we use a slightly different equation that considers the width of the gouge layer. And that's because since those contacts are bigger, they're a millimeter long, the heat penetration depth is a little bit larger. And so we want to take that into account when we calculate the temperature of those millimeter scale contacts. And then again, the heat generation rate is just turned off and on, informed by our millimeter scale sliding geometry. And what we wanted to do, which in hindsight might have been a little lofty, was identify a unique set of material parameters for Westerly granite and the flash weakening model. And so I looked at over 240 unique parameter combinations where I varied my fully weakened friction coefficient, my asperity dimension at the micrometer scale, my weakening temperature at the micrometer scale, and then my weakening temperature at the millimeter scale. But I used that 101 millimeter asperity dimension for the millimeter scale contact that I know from my thermography, and also my contact shear strength. To limit the parameters in our model, I used a fixed ratio of my contact shear strength to my asperity dimension. So that contact shear strength is tied to the asperity dimension. And this relation was just the same one that was used in Rice's original derivation. So looking at the model results, here we've got friction coefficient plotted versus velocity, and then plotted versus displacement. And these are the same data. The measured data is shown in this blue solid line, and our modeled data are shown in the dashed and dashed line. So this dashed dot line is a model that only assumes weakening at the asperity scale. And this brown dashed line is a model where weakening occurs at both the micrometer and millimeter scale. So it's our multi-scale model. And the first thing we see is that the multi-scale model outperforms the traditional conventional asperity only scale model, but both of them overestimate the amount of weakening. So it's weakening faster than the mechanical data shows. And then it predicts more weakening than we see in the mechanical data. What is interesting though, our multi-scale model, in addition to predicting the steady state friction coefficient, we have at the end of sliding in these decreasing velocity experiments, these spontaneous stick slip events, large stick slip events that occur after the end of sliding. And this is before we reach a mechanical stop in the apparatus. The single scale model doesn't really predict those events at all. This decrease here is just simple rate and state equations, but the multi-scale model does predict a small weakening event. You can see it here in displacement space, but also in velocity space. You can really see it more clearly here. And so it seems like using this multi-scale flash weakening, considering weakening at the asperity and at the millimeter scale, is certainly an improvement to the flash weakening model. But it's still not sufficient to identify a unique parameter set, constitutive parameter set for Westerly granite. So here on the left, this is friction versus velocity, and again, displacement for 2 of our experiments. And these are showing the best fit to those individual experiments. So when we look at the non-unique best fits, it does a pretty good job. But if we try to fit one parameter set to all of our experiments, that's what we have here on the right. And what we see is that we don't really fit all of the experiments well. In this instance, I'm particularly overestimating the amount of weakening in the lifetime equals rest time experiment, but it does a pretty good job for the lifetime is greater than rest time experiments. And I'll say that this overestimation of the total amount of weakening in our steady state friction, it increases as sliding velocity is increasing. So it's most extreme in this experiment where our sliding rate was 900 millimeters per second. It's less extreme in some of our lower velocity experiments. So taking all this together and combined, first, we saw that surface temperature is inhomogeneous at high sliding rates, and this reflects inhomogeneous normal stresses. And there's this transition from high to low normal stress contacts. This reflects wear and plowing. If we incorporate this inhomogeneous stress and temperature distribution into a flash weakening model, it certainly has improved, but there's still transient and hysteretic friction that we're not capturing. And so the model fits right now, in particular, they're not sufficient to identify a single, unique set of constitutive parameters for Westerly granite. So this kind of leads us to two big takeaways and points. The first is that it's clear that wear processes are important, and it would be worth developing some constitutive equations for wear processes to fold into numerical modeling for dynamic weakening, particularly if we think about during the early stages of sliding when we have those high stress contacts, those also have high wear rates. And so that's serving as an energy sink at the beginning of the experiment. So in this modeling, we're assuming that all the work is going into frictional heat, but we have some of that work going into the wear process. And so it could be that in order to really describe the transient and hysteretic friction we're seeing in the lab and to better model earthquakes in nature, we need to develop some constitutive equations for wear processes. The second point is that this systemic overestimation of weakening that we see in our experiments, we think it could reflect a secondary weakening mechanism that's happening. Since it's most extreme in our highest velocity experiments, and we're overestimating the lifetime equals rest time experiments. So those are the experiments with the lower rest time. If we had a longer length scale weakening process that's maybe at the millimeter or even the centimeter scale, our lifetime greater than rest time, those short rest time contacts, they're going to be in contact more frequently. And so they would be impacted more so from any secondary weakening process than our lifetime equals rest time. But since I'm forcing these fits to all the experiments, the fact that it underestimates the lifetime equals rest time, I could either underestimate this set or I could overestimate the lifetime equals rest time or underestimate the lifetime is greater than rest time set. But either way, it suggests that there could be a secondary weakening process. So, in addition to thinking about millimeter scale weakening in flash heating context, we should also consider millimeter scale processes and above that could be happening in addition to flash heating and weakening. So with that, I will again thank the conveners for inviting me and then open up to any questions.